Hi, I'll be covering problem D in CodeCraft 2022. In this problem, you're given an array of n integers, and you're asked to verify for this inequality for all pairs of indices where I is less than or equal to j. This inequality basically states that we have to check for every subarray and verify that its sum is less than or equal to its max. The constraints on the length of the array is given as 2e5, while the elements in the array can range from -29 to 1e9. Now, the simplest way to approach this problem would be to just compute all the subarrays and verify the inequality. So say we had an array you could check all subarrays of length 1, then length 2, and so on. Computing the sum and the max of each subarray takes O of n time, and there are n square subarrays in total, which would give this algorithm O of n cubed time complexity. However, we could reduce this by iterating over the subarrays and using precomputation. So we could iterate over this subarray, then this, and use a previous subarray to compute the current one. This reduces down computing the max and the sum of each subarray to O of 1. But the number of subarrays still remains at n square, giving us O of n squared time complexity, which is still not sufficient. A better way to think of this problem is to iterate over the subarrays in a different order. Say we had this array. We can instead iterate over each element and find out in which subarrays is this element the max. So say we're on the third element. We have to find out in which subarrays will this element index would be in the max in this subarray. So how do we do this? Assume we knew what was the next greater element and the previous greater element for each index. So say for this element specifically, this was the next greater element and this was the previous greater element. This would mean that any index in this range and in this range, if the starting index is one of these and the ending index is one of these, then we know for a fact that that this element would be the max in all of those subarrays. So if we marked the previous greater element index as p of I and the next greater element index as b of I, assuming that the current element is I, the starting index would have to be between p of I plus 1 and I, while the ending index would have to be between I and bi minus 1. Now, how do we compute these indexes? Because if you compute it the naive way, it would end up taking n squared time again. Well, there is an algorithm called the next greater element algorithm, and this allows us to compute the next greater element index for all elements in the array in O of n time in total. You can again modify that to make it the previous greater element algorithm, and that will be done in O of n time as well. So this algorithm fits well inside the time complexity that's required. Now that we have this, how do we optimize the queries in checking all the subarrays? Because we'll still end up checking all n square subarrays. We can do this by breaking down a single subarray. Say the greatest element in the subarray is I. We can talk about the left part of the subarray as x and the right part as y. Since this inequality is supposed to hold for all subarrays, we can list this inequality down as this. the left part of the subarray plus the right part of the subarray plus the element that is the max, which will give us x plus y plus a of I. And this is supposed to be less than a of I. Again, we can cancel this out, which would give us the inequality x plus y is less than equal to 0. But this is for verifying if this inequality holds for every single subarray. So we could instead check for this inequality. And if this inequality holds for any subarray, then we know for a fact that we have to output no. Now when does this inequality hold? Since we have two elements and the sum has to be greater than 0, it implies that one of them at least has to be greater than 0. That means either x is 0 or y is greater than 0. So say we have an array like this, and I'll put some elements. And say that this is the current element that we're on, this is the next greater element, and this is the previous greater element. All the possible arrays of x would be something of this style, and all the possible y subarrays would be this, which basically indicates that the x subarray has to end at index I minus 1, while the y subarray has to start at index I plus 1. So all we have to do is check for all of these subarrays and check if any one of them is greater than 0. Because if they're greater than 0, you can just pair them up with a of I and break the inequality. So say x was greater than 0. Now we have a of I plus x, and we don't care about the y section, and we'll try to verify if this holds true. But x is greater than 0, so this won't hold true. And you can do something similar for y. Therefore, it's sufficient to just find any one of these prefixes for a certain element I and check if they're greater than 0, or these ones for y. But how do we exactly check for all of these values? Because if we checked it the naive way, it will end up taking O of n time for each index, which will give us O of n squared again. As you can see, this is a range of elements, and these values correspond to prefix sums. So you could extend this and calculate these values by just subtracting the prefix sum at this element. So we can see that we just have to make a range query. Range query over the prefix sums. And if you see range query, then we most probably have to solve with a 7 tree. So say we had a prefix sum like this, and yeah, just going to name it, and say that we're on element I, so around here, and the next greater element index was this. Then we'd have to compute all of these prefixes. So how do we do that? All we have to do is subtract prefix of I and apply it to all of them, and you'd end up getting a prefix starting from this index, which is what we want. And as you can see, we just need one of them to be greater than 0. So instead of checking for all of them, we could just find out what's the max among these. So what we have to do is a max range query over the prefix sums. So all we have to do is make a query like this. Say we had a segment tree that was built on the prefix sums. So we'd want to make a query from I plus 1 to b of I minus 1, which is the next greater element index. So it would cover all of these prefixes. And we want the prefix sums to start from here. Hence, we have to subtract prefix of I. And this value will give us the max of all of these. And if any one of them is greater than 0, then we know for a fact that the inequality does not hold for all the subarrays, and we can output no. Of course, this is only for the prefix sums. For the left side, for calculating all of these, you'd have to do a suffix array. So you just create something similar, but just in the reverse direction, and make very similar queries. So if say that we had a suffix array, and we try to make queries to that as well for verification, then the queries would look something like this. It would range from p of I plus 1, which is the previous greater element index, and go up to I minus 1. And we want the suffixes to start from I plus 1. So I minus 1, my bad. So instead, we'll subtract suffix of I and verify if it's greater than 0. So this is for prefix, and this is for suffix. And if any one of them hold true, then we output no, else we output yes. As you can see that we're making two segment tree queries per index, and we have n indices. So the total time to complexity taken by the segment tree is O of n log n. The other computations that we're making is the next greater element and the previous greater element. So I'll just label them segment tree and next greater element, and one more which is the prefix sums, which will take again O of n. So in total, the time complexity ends up to be O of n log n, which fits in the time complexity.